College algebra students, we are entering into a fundamental section for college algebra. 3.3 deals with graphs of parent functions and transformations. This is a topic that we will be using all semester. In section 3.3.1, we're going to develop a library of parent functions and parent function graphs. Any graph that we construct in Unit 3 will first begin with one of these 6 basic functions. So it's really important that you can generate these parent functions and recognize them easily. We'll begin with the identity function. The most fundamental or the easiest linear equation in 2 variables that we could write is the function y equals x. Now, if I wanted to write that in function notation, I could call it f of x equals x, or in 2 variable notation, we have y equals x. What we want to do is determine the graph of this function in the plane. To do this, we're going to go to a very basic approach to graphing, and that is plotting points. So what you see over here is called a t-chart. We're going to choose some random values for x, and I'm just going to choose small, easy to work with numbers, such as -2, -1, 0, 1, and 2, but really you can choose any x value over there. Then we're going to plug those into the function to see what comes out for y. So if my equation is y equals x, and I plug in my first value, -2 for x, notice y is identical. Y is also -2. The same thing's going to happen in my equation y equals x. If I plug in -1 for x, do you see we're going to get the same thing for y? That's why this is called an identity function. X and y are identical. So if x is 0, y is 0. If x is 1, y is 1. And if x is 2, y is 2. So this generates a list of ordered pairs that I can plot in the plane to begin looking at the pattern of the graph. So let's plot our points. -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. That's enough points to determine. It looks like we have a straight line. So very carefully, I'm going to connect the dots. If you have a ruler, use a ruler. And this is our most basic linear function. It's called the identity function. Now, if I look at this line, and I figure out what are the x values used on this graph, what's the domain, I can see the leftmost x value is -infinity and the rightmost x value is infinity. So this domain is -infinity to infinity. So the idea of this section is any other linear function, more complicated than this basic y equals x function, will also be a straight line. It will share the same nature as this linear function. Let's look at our next function. Next, we will consider a quadratic function. The most basic or the easiest quadratic function we could think of is y equals x squared. Now, in function notation, this would look like f of x equals x squared. So we are dealing with functions. And this time, we're going to plug in x values, -2 through 2, into this new function. So if y is equal to x squared, and I plug in -2 for x and square it, notice the corresponding y value is going to be 4. Or if I plug in x equals -1, the corresponding y value is going to be +1. So notice I'm just squaring the x values to get the corresponding y values. So 0 squared is 0, 1 squared is 1, and 2 squared is 4. Anytime you square a number, it turns out to be positive. Now, let's plot these points in the plane. First one is -2, 4, -1, 1, the origin 0, 0, 1, 1, and 2, 4. Okay, so this generates a basic parabola. So I'm going to connect the dots with a smooth curve. I don't want it to look like a V. I want it to be a nice smooth curve. Kind of messed up that left side there. Let me try again. All right, that's a little better. This is our most basic quadratic function. So the idea is another quadratic function that's more complicated, maybe something like 2x squared plus 3x plus 5, is going to be related to this function. It's going to be a parabola, even though it may open up or down, or it may be shifted elsewhere in the plane. It's going to share the same basic nature as this parent function, y equals x squared. Now, let's identify the domain of this function. If I look at the leftmost x value or the rightmost x value, notice the parabola continues getting wider and wider. So our domain is negative infinity to infinity, okay? We are developing the parent functions that are also known as power functions. I have a little typo on my notes here. Sorry about that. Change this word absolute value function to cubic function. So we're going x to the power 1, x to the power 2. Now we're at x to the power 3. So again, if I want to look at this cubic function in function notation, it's f of x equals x cubed, or we can just think of it as the two-variable equation y equals x cubed. This time, I'm going to plug in my x value and cube it. So negative 2 cubed is negative 2 times negative 2 times negative 2. That gives me negative 8. Or if I plug in negative 1 and cube it, this time we're going to get negative 1. So we're cubing the x values to get the corresponding y values. So can you help me fill out the table? What is 0 cubed? 0. 1 cubed is 1. Are you with me? And 2 cubed is 8. So let's plot these 5 points in the plane. So again, this is a very fundamental way of graphing. If you don't know what the graph looks like, you can always plot points and begin to determine the pattern or the shape of the graph in the plane. Okay, so here's the basic shape, and kind of squiggles its way through the middle. Make sure that you get arrows on the endpoints of your graph to indicate that that pattern continues beyond the grid that we can see. So this particular domain is also negative infinity to infinity. So if I look at the general idea of what we just learned, we've got the first 3 power functions, x to the power of 1, x to the power of 2, and x to the power of 3. The linear function, the quadratic function, and the cubic function. The linear function, or the most basic linear function, is the identity function, has the domain negative infinity to infinity, and so do the quadratic and cubic functions. Now, the shape of the quadratic function, this U shape, is what we call a parabola, and the shape of the cubic function, it doesn't really have a name, so I'm going to call it a squiggle for lack of a better word. A cubic, or you'll probably hear me refer to it as a squiggle. So those are our first 3 basic parent functions. Now, let's move on to root functions. We've done the power functions. Now we can examine the root functions. Oh, let me go back one more little step here. I want to show you one more thing. On our calculator, we're just going to stop at these 3 power functions. Let's look at what happens when we continue increasing the power. So I'm going to go to y equals, and I'm going to graph x squared, and notice it's just a basic parabola. This matches what we did by hand, and let me remind you, you can go to the table, second table, and you can see a list of ordered pairs, though. Those are the same ordered pairs that we generated by hand. So know that you've got the support of your calculator to check your parent functions. Now, I'm going to go back to y equals, and I'm going to arrow down to y2. We did x cubed. Let's see what x to the 4th looks like. So if I graph x to the 4th, y equals x squared is blue. Notice I get another parabola. It's just a little bit steeper, okay? In fact, this happens with all even powers of x. So if I look at any even power of x, it's going to basically be a parabola. It just gets steeper and steeper as we increase that exponent, okay? Notice the same thing is going to happen with our odd power functions. So let me clear this out. We'll start with x cubed, x to the 3rd power, and we get our squiggle shape, like what we graphed by hand. And then I'm going to go back to y equals, and I'm also going to graph x to the 5th. So I'm just looking at odd powers here. So x cubed is in blue, x to the 5th is coming in red. Do you see how it's got the same basic shape as x cubed? It's just steeper. So that happens with every power function. Even power functions graph as parabolas. Odd power functions graph as those squiggle shapes. So really, we know a lot if we know those first 3 power functions. Okay, let's go ahead and move on to our root functions, starting with the square root function. Now, we have learned how to find the domain of a radical function. I want to do that first. To find the domain of a radical function, remember we take the radicand out and set it greater than or equal to 0. Sometimes we have to solve for x, but in this case, it's done. I can go ahead and convert that to interval notation. In interval notation, we would get bracket 0 to infinity. That is our domain. What that's telling me is I can only plug in positive numbers for x or possibly 0. So if you'll notice over here in our t-chart, we only have positive values. If I try to plug in a negative value, that's going to give me an imaginary number, and there's nowhere to put an imaginary number in the real plane. So we're only going to be choosing positive numbers. And also notice I've chosen convenient values that are perfect squares so that I don't have to worry about plotting decimal values. So please memorize these points. You'll want to generate this with ease. So if x is equal to 0, and we plug 0 into the radical function and simplify, we would see that y also equals 0. If we plug in 1 for x, the square root of 1 is 1. And by the way, we're not taking the square root of both sides, so we don't have to recognize plus or minus. The only time we need the plus or minus is when we actually apply that operation to 2 sides. Okay? Next point is 4. The square root of 4 is 2. And the square root of 9 is 3. So because we used perfect squares for the x values, the y values came out nice, neat integers, so I don't have to, again, worry about decimals. But they're not equally spaced on the grid, so be careful when you plot your points. So we have 0, 0, 1, 1, all the way out to 4, and then 2, and then all the way out to 9 and 3. So in this case, we get half of a sideways parabola. Okay, why is it not a whole sideways parabola? Well, a whole sideways parabola does not pass the vertical line test, so it would not be a function. Okay, so the square root of x is a half of a sideways parabola, and its domain is 0 to infinity. So again, the idea of this section, another radical function may be more complicated, like 2 times the square root of x plus 1. Well, it's going to have this same basic shape. It's going to be a half sideways parabola. It may open the other way, it may be reflected, but it's going to have this basic nature, okay? Next, we're going to pass from the square root function to the cube root function. You'll have to correct my errors in the notes again. This is the cube root function. Sorry about that. Unlike a square root, it is legal to plug a negative under a cube root. If I plug in -8 for x, I'm evaluating the cube root of -8, and that is -2. So it comes out to be a real number. So for that reason, we can plug in negative values. The cube root of -1 is -1. The cube root of 0 is 0. The cube root of 1 is 1. And the cube root of 8 is 2. Notice over here I have used perfect cubes. Again, to avoid getting decimal values, like finding the cube root of 2. That's kind of a mess. But our numbers are nice and neat. This generates a good parent starting function. Those numbers should be familiar. They should look like what we did for the power function, x cubed. They're just reversed. So let's plot all of our points. Notice we get a sideways squiggle. Okay? So the x to the 3rd power was a vertical squiggle. The cube root function is a sideways squiggle. If you'll notice, all the x and y values just switched positions. We're going to learn later that those are inverse functions. Now, observe there is no leftmost point, there is no rightmost point, so the domain of this function is -∞ to infinity. If you want to find the cube root on your calculator, this is a good thing to know. Go to your y equals. I'm going to clear out what I have here. And I'm going to access the cube root from my math button. So I'm going to press math. I'm going to choose option number 4. And that puts the cube root on my screen. And I can type in the argument x. And it generates our sideways squiggle. Okay? Every graph that we construct is going to begin with one of these parent functions. So it's really important that you know how to generate these basic shapes. Notice again, if I look at, for example, x equals 2, see how we get out a decimal value? By hand, it's nicer to have integers as you plot points. That's why we chose perfect cubes. Okay? Our last power function is not the cube root function. It is, again, sorry about the typos, absolute value function. Y equals the absolute value of x. So when we plug in any of these numbers and take the absolute value, the result is positive. Have you ever wondered why absolute value always turns out positive? It's simply because absolute value represents distance. Okay, so the distance between -2 and 0 is 2, and the distance between 2 and 0 is 2. So I'm just measuring the distance of all of those points to the origin. That's what absolute value is for. It's easy to evaluate. The absolute value of any number is always positive. So when we plot these in our coordinate plane, we get an interesting shape. This generates a V shape. Okay, the parabola that went with the x squared is a nice, smooth U shape, a curve through the origin. But the absolute value V shape is a sharp turn or a corner at the origin. Okay, the domain of this function is also -infinity to infinity. Did you notice that the domain for all 6 of our parent functions is -infinity to infinity except for our square root function? So that's going to be easy to remember. Let's make sure you know where to find absolute value on your calculator. I'm going to press my y equals to graph, and then I'm going to go to the math menu again, arrow to the right to highlight NUM for number, and option number 1, ABS, that is absolute value. So I'm just going to press enter. That puts the absolute values on the screen, and I can type my variable key x and graph, and we will end up with our absolute value function. Those are the 6 basic parent functions. Other graphs that we construct in Unit 3 will begin with these basic parent functions. So the idea is a more complicated absolute value function is going to share the same nature as the simplest absolute value function, although, again, it may be opening in a different direction. It may be translated elsewhere in the coordinate plane. So what we want to do next is associate these more complicated functions with their parent functions. So let me explain it this way. For those of you out there that have kiddos, or if you don't have kiddos, you can think about your parents. If you look at your kids, don't they sort of look like you? They probably look like you. Maybe they look like your significant other. They probably act like you a little bit. But sometimes they grow up, they move out, they get a job. They look like you, but they're different still. That's the idea with these parent functions. So I like to call this section, Who's Your Daddy? Okay, we got to have fun with this, right? So look at example 1a. Y equals -2 times the absolute value of x plus 1 minus 7. I want to know who is the parent function, who's the daddy for that function. Well, I'm going to ignore all of those details, the -2, the +1, the -7, and I want to know what's the major function, what's the nature of that function. The main operation going on there is the absolute value, right? The +1, -7, I'm going to ignore all of that. I see it's an absolute value function. So this absolute value function, even though it's going to be a little different, is going to share the same basic nature as the parent function, y equals absolute value of x. So I'm going to say the daddy of this function is the absolute value function. So I would start by graphing the basic absolute value function, and then later in this section, we'll learn how to interpret what does the plus 1 do? What does the minus 7 do? What does that negative 2 do? It's going to edit the graph just a little bit. Okay, let's look at example B. Y equals the cube root of x minus 4. Again, I'm going to ignore all the details, the constants that are there, and I want to know what is the basic nature of that graph. Who's the daddy? Can you figure it out? I hope you said cube root of x. Okay, so when I graph cube root of x minus 4, essentially it's going to look like this. It's just going to be shifted a little bit. Okay, who's the daddy for example C? The main operation there is x squared. Okay, so when I graph it, it's going to be a parabola, but this one happens to be opened down. It's going to be a little wider than the original, and it's going to be shifted to the right. And we'll learn how to do that soon. Who is the daddy for example D? The parent function there is x cubed, so it's going to look like a vertical squiggle. So we are associating these more complicated functions with one of the 6 parent functions, the list that we just completed on the previous 2 pages. To understand what these graphs look like, they're going to share the same nature of the parent function, although just a little bit different. Let's see if we can do that with graphs. Looking at example E, I want to figure out who the parent function is. I notice it is a parabola, and remember, if we come back over here and we look at the parabola is our quadratic function, y equals x squared. So we'll say the parent function for this parabola is y equals x squared. Remember, when we graphed our parabola, the basic parent function went through the origin. In fact, I'll just graph it here. This was our parent function. So we're recognizing this resulting function has the same nature as the x squared function. This one just happens to be a little taller and skinnier. It's moved out. Its vertex is in a different place, but they share the same basic nature. Looking at example F, we have half of a sideways parabola. Do you remember which function that one was associated with? That was our square root function. So our square root function did something like this that we graphed. This one is sharing the same basic nature, but it is shifted. How about example G? Notice this is a sideways squiggle. This one would be associated with not the cubic function, but the cube root function. And finally, example H, it is a V. It opens down, but it is still a V shape. This guy goes with absolute value. Remember, V shape goes with absolute value. Value starts with V. So this is how we're going to begin graphing our more complicated functions. We will figure out which parent function it is associated with, and then we will look at how the operations in the function actually change the graph. We'll do that in the next video.